Hi, everyone. My name is John Cypress. I'm a TA for the Department of Chemistry, winter quarter 2023. So today I'll be going over the introduction to lab techniques, the data analysis, and kind of give you some guidance on how to do these post-lab calculations if there's any confusion. So I'm looking at this first page of the data analysis of Introductory Laboratory Techniques Lab, right? First, you want to calculate the mass of water delivered in each of these trials. So how would you do that? So in the beginning of the lab, right, you should have measured the weight of your empty Erlenmeyer flask, and it should be around 93 to 90, like 7-ish grams. I'm just going to make some numbers up here. So let's say that it is 93.274 grams for this Erlenmeyer flask. All right, so that was the empty flask, right? Then, with your pipette, you pipetted 10 milliliters of water. Right, so now you have some water in your flask like this, and you took the mass, right, of this flask, and you should have gotten about 10 grams added. Again, I'm just going to make up a number here. So let's just say that this volume, or sorry, this mass ends up being 103.164 grams. That's what I measured it to be. Okay, so now that I have this, right, to find the volume or the mass delivered, not the volume, the mass of water delivered is going to be this 103.164 minus 93.274. Right, these are both in grams. And in this case, it ends up being 9.890 grams. Right, so that's how much water got delivered in terms of mass. Now, you were supposed to pipette again 10 more milliliters. A note to be careful, right? Make sure you put the mass of the Erlenmeyer flask, not the volume of the Erlenmeyer flask on Achieve, right? Otherwise, it's going to ask you to put in like more than 125 milliliters. A few people were having problems with this. So make sure you're putting the mass right as it asks, not the volume of your flask. So now in the next trial, you added 10 more milliliters of water. And you should have about 10 more grams, right, added to your flask. So let's say that now this weighs to be 113.157 grams. Now to find the weight of delivered of this step, you take the difference between these two flasks, right? You're adding the water. You don't want to account for all the water. You just want to account how much water was added in that one trial. So you take the difference between this one, where you just added more water, and the one before, where you had some water in it. So the mass of H2O delivered in this one, right? Let me put a 1 here, and then this is E2 for the second step. Right, this is going to be 113.157 grams minus 103.164 grams. All right, and then this ends up being 9.993 grams. Right, if you take the difference between this one and this one, you're going to get the wrong answer. You're going to get up like 20, right? Which is the total amount of water added, not the one delivered in that one step. So let's go down here. You would do this again, right? And it's the same procedure. So you added 10 milliliters, right? And you should get about 10 more grams. And then for this third one, right, the mass of water delivered is going to be 123.172 grams minus 113.157 grams. All right, so this ends up being 10.015 grams, right? So make sure when you're doing these, right, you're taking it between trials, not the total weight, or you will get this wrong, right? Because then you would be doing 20 from here to here and then dividing it by the volume of 10. I've seen this happen, and then getting the wrong density. So now that you've done this, so you want to calculate the density for all of these. Right? And then the way you're going to use that or do that is with this formula, right? Density is equal to mass over volume. So for trial one, right? And this is trial one. This is trial two. This is trial three. For trial one, the mass delivered is 9.890 grams. The volume delivered, assuming you use the pipette correctly, right, is going to be 10 milliliters. And then you should get some density. So that is my trial one. Right, and you would do this for all of these, and then I'm just going to skip ahead when I finish all these. Okay, so now that you have all your densities, right, what you want to do is just average them. So you average your densities, right? This is 0.989. Over here we have 1.015. And then we have plus 0.999. We're dividing it by 3. This is how you average it. So let me actually cut this. Put it over here. Now, in the back, right, of your lab notebook for the data analysis part, you can look at, I think it's on page A23-ish. Give me 1 second here. Yeah, statistical treatment of data is what they tell you. Okay, let me just find the correct page here. So it's page A33. So on page A33, right, you have this formula of x bar is equal to this sigma symbol times xi over, and not times, but sigma symbol and then xi. So what this means, for those of you that want to know what this means, this is your average value, right, of whatever you're measuring, or looking at. This here is the number of values that you're averaging. And then this up here is the sum of all values. A more proper way to write the top there would be like this, with a sigma of I equals 1 to n of xi. So what this means is you start at 1, right? I equals 1. What does that mean? Right? So x1 is trial 1. Right? x2 is trial 2. And then so on and so forth until you get to however many trials you have, right? So you're adding up all the different trials with their respective values. Value. And then just dividing it by the number of trials you have, right? For averaging. So in my case, the average density is equal to that. I'm taking my density values, adding them up, and then doing that. Okay, next is a standard deviation, right? So that is your average. So your standard deviation has a formula, again, on page, let me do this in red, A33. Has a formula of S is equal to this thing right here. And again, we'll talk about what this is exactly. So, right, this X bar, that's still your average. It's still the same thing that it meant before. This new S, this is your standard deviation. It essentially measures, right, on average, how far away are your data points from your average. So high standard deviation typically indicates poor precision, right? Versus a low standard deviation indicates a high precision. So if we're looking at this, right, it's kind of the same terminology as before. So we have this xi, and we're summing all these things up. So what this is, again, this is each trial. So x1 is your first trial, x2 is your second trial, x3 is your third trial. In this case, you only have 3, right? You may have 5, 10, 20 in the future, probably not 20, but you can have more than 1 or 2 trials, right? You can have as many as you want. So the way this works is you have to do each of these subtractions separately and then square them. So you're going to get a big, let me rewrite this. I equals 1, it goes to n. Again, this is just to show that it goes to however many trials you have. That is the more appropriate way to write it. So you start at your first trial and you go to n however many trials you have. All right, now the way this would work, right, is if I were to plug this in this case, or in this lab, right, how this would look is like this. And again, just to note, this means a sum. You're summing over all these values. So in this lab, right, you would have your first trial value minus the average value, right? And these are for density. Squared plus second trial value minus the average squared plus the third trial value minus the average squared. Put this all over 3 minus 1, right? N is 3. You have 3 trials. And then you would just plug all the values in. So in this case, in my particular case, right, with the numbers that I have, I'm going to be using these density numbers, right? So first is I have 0.989, and what you would want to do is that you should, let me go back. You should use unrounded numbers for your calculations. You should only round at the end. So in this case, right, you would want to actually use your unrounded values. For the calculation. Okay. So that in my case, my unrounded values are not too different here. So for trial 1, it's actually that. So here's that. And then my average is, let me find the unrounded value here. Oh, I actually didn't even plug this in. So, right, I have to take my density. I totally forgot to plug this in. 994. Thing. Oh, 999. So this ends up becoming 1.001 grams per milliliter, right? And this is my average density, which I'm going to have to use for this calculation. So over here, right, I'm going to use 1.001. That is my unrounded value. I'm going to add these all up, right, for trial 2. It's 0.9993 minus 1.001 squared plus, and then we have 1.015. Oops, this should be 0.2 here. But what I would actually plug in is going to be 1.015 squared. And you could put the units here. I'm not going to do it just because it's so much extra writing, but it can help you check if you have the right units, right? So you're taking the square root of the unit squared, essentially, is what happens. So you should get the same units as density. Then this is over 2, right, in this particular lab. So for this case, my standard deviation, let me plug this all in. And that should be a 1 at the end here. Don't know where I got that one from. 0, 0, 1. Or 2. Okay, so your standard deviation should end up being, in this case, in my case, my standard deviation is 0.013. I'll do 3 sig figs. I think on Achieve, they may want 4. I'm not entirely sure, but you would do this to the number of sig figs that Achieve wants. So I just don't know what that is. Okay. So that's it for standard deviation. Now we have to use the 90% confidence interval formula. Again, this is going to be on page A34 now. It's on the next page. And let me actually show you. It's going to be right here. Right, this is going to be where you get these formulas from. So there's your average formula. There's your standard deviation formula. I just explained what those are. And now we're going to be using this formula right here, this confidence limit one. This one, do not worry about it. This one is what we're going to use for the 90% confidence limit, since that's what they give us. So I'm actually just going to copy and paste this. And use this. All right, so if we're looking at this, right, we have our standard deviation here. That's the S, still means the same thing. So you have that number now. You would just plug that in. You have your N, your number of trials, right? You would also just plug that in. Let me just write these in. And then you have your T critical, right? You would look at the table for this. What table? That table right down here. So in this experiment in particular, right, you have 3 trials. So we're going to use a T critical of 2.92. So in this lab, we have 3 trials. So a T critical value is 2.92. Okay. So all we would have to do is this confidence limit is equal to 2.920 times 0.0131, right? You would use the whole decimal. So let me actually write in the whole thing here. 0.93708 is what I would use. And then you have to divide that by the square root of 3, right? 3 trials. And then this becomes 0.0221. And that's it. So you're going to repeat this, right, for each data, essentially. So this is the same procedure for the burette calculations and the beaker calculations. right? They're literally the same. So you're finding the difference of water that you added between each, right? I think in the, I'm not sure in the beaker, I think you pour it out. But it's going to be the same thing here. In the burette, you don't empty your flask, you just end up keeping the water in there. So it's going to be the same. So it's the same procedure here, right? Now there is one extra step for the burettes. So for the burettes, right, to find the volume delivered, you must do your initial burette volume reading, right? That should be in milliliters. And from that, actually, whoops, I'm getting this backwards. You take your initial burette volume reading and you subtract that from your final burette volume reading. Right, and this should also be in milliliters. So you should have, for this lab, measured the initial and final volume of your burette, right? So I know I mentioned you don't have to get it exactly to 12, right? You shouldn't be doing that, but you should just pour it to some height, right, that you can read. So like 3 is a good one. So you stop at that 3 mark, and then as you drain out the water, right, you would want to go to about 15 to deliver 12 milliliters for this lab, right? So 15 minus 3 gives you 12. Now, if you're above or below, right, it doesn't matter as long as you read it correctly. Because if you deliver a little more, then you get a little more mass, right? And you would measure that, and then that would play a role in your density calculation. If you deliver too little, then you get not as much mass, which you should still have pretty much the same density calculation. So as long as you're reading it correctly, right, it shouldn't affect your density results. So that's with the burettes, right? Again, don't fill it up to exactly 12 or exactly where you're using it. I think the easiest example to give is it's talking about burettes, right? They are kind of backwards from what you're used to. So typically you fill up like a graduated cylinder to like 10 milliliters and then you pour it in, right? And then it's all in there. But a burette, right, you're actually draining out volume from the burette. So if you start, and don't have to get to 0, I would recommend against it. It doesn't have to start at exactly 0. But if you started at 0.00 milliliters for your burette, right, that is telling you essentially how much volume you have delivered right now, right? 0. Now, if you drain some out, like 5 milliliters, right, you'll see the meniscus at the 5. That means that you have now delivered 5 milliliters, right? So that's where the readings come from, and that's why you're going to take final minus initial. It's the same thing, 5 minus 0. In this case, right, you would start at 3, and now you're draining out 12 milliliters to get to 15, and then you do 15 minus 3. So that's why you have to take an initial and the final reading for your burette all the time, right, no matter what you're doing with it. So you take final minus initial, and then that is equal to the volume delivered by the burette. So that is the only extra step for that. Again, it's the same procedure. You're just finding the mass between each trial. I think in the beaker you empty it, so you would just do them all separately. And then, but I'm not sure, right, check your lab manual for that, double check. But for the burette and the flask, right, specifically, you would just take the weight between each trial, calculate the density, then calculate the density for each, then calculate the average density, then calculate the standard deviation, right? So average density, then your standard deviation, then you use your standard deviation for the 90% confidence limit, which we got over here, right? And then you would repeat this 2 more times, really, with 1 extra step for the burette portion. Okay, so that is it for the volume part, right, for delivering water and the density of water part of this lab. Now you have to do the manganese sulfate part of the lab, right? So let me just open up my notebook here. So we're not going to really need these formulas. Let me actually just go on here. All right. So, oh, actually, one last thing. I missed it here. Right. It says that you have to find the relative error of the density of water. So what you're going to do is, let me first copy and paste this, right? To find the relative error, slow down. Find the relative error, right? All you want to do is use this formula. So experimental result, the absolute value of your experimental result minus the accepted value over the accepted value. The accepted value is going to be different depending on what you measured for your water temperature, essentially. So if you go to page, let me find it. Let me pull it up on here so we can see it. Over here on page 6, you're going to use this table, right? This table tells you the volume occupied by 1 gram of water at different temperatures. So you can calculate the density from here, right? So let's say the accepted value at 18 degrees Celsius is what, right? We're going to use D is equal to mass over volume. In this case, this is 1 gram of water, 1.000 grams over, at 18, it's 1.0024 milliliters, right? So the accepted value is 0.99276 grams per milliliter. So that's your accepted value, right? I guess to be more appropriate, I should use 5 sig figs here. 1 grams per milliliter. So you're going to do this for whatever your temperature of your water was, right? If it was 19, do the same thing. It's just the volume changes, right? For 19, you're doing 1.0026, so on and so forth. So I am going to use this value for my calculation. And this is at 18 degrees C, right? You should be using your measured temperature. Accepted value. So I'm just again arbitrarily saying that this is my accepted value. So the relative error is going to be the absolute value. Now my experimental value, which one is that? Right, do I pick trial 1, 2, 3, 4? Or I don't have a 4th one, but in this case, you're just going to use the average, right? So you use your average density calculation here. That is going to be your experimental value, okay? All right, so my experimental value is 1.001 right? That's grams per milliliter minus my accepted value, which is 0.99761 grams per milliliter, all over 0.99761 grams per milliliter times 100%, right? This is seeing how far off I am from the actual value. So what percent off am I? All right, again, you would use unrounded numbers here. So whatever unrounded numbers you have, please use those. So I end up getting 0.34%, right? That is very close. So I made my numbers up. So should be, right? That is it. Same procedure again for all of these. For the burette, you have one extra step, right? But it's the same thing, so I'm not going to go through all of them. So now we're going to do the manganese sulfate part. So looking at the lab manual, right, we, excuse me, it says, what is the mass of grams in your MnSO4 sample before heating? So, I'm just going to copy and paste all these. I think it would be easier to follow like that. So what is the mass in grams? Before heating. So this is going to be what you weighed out, right? I was thinking of the crucible. Right? This is what you weighed out. So in my case, I'm just going to make up a number, right? So let's say I weighed out 1.123 grams of MnSO4. So this is my number, right? Making it up. It'd be whatever you have. So that is what you weighed out into the weighing boat. Right now, next is, what is the mass in grams of your sample after heating? So how would you do this? Right, so similar to the crucible thing. So first, let me copy and paste this. All right, so first, you have your empty crucible, right? And then, right, this is after heating. You should have done it after heating. So that's your empty crucible, and it has some sort of mass, right? Now, you should have afterwards added the manganese sulfate. Or the manganese sulfate hydrate. Right, and you would have had some of that pink stuff, right, in your crucible. Okay. So, and then this is, again, before heating MnSO4. Then you should get the weight after heating. So now this is crucible plus MnSO4. not MnSO4 H2O. Why? Because we're assuming that all water evaporated. So you have to assume that all of that water evaporated after heating this, right, for this to make sense. So assume all of it evaporated. Whether or not it did is another question, right? Probably didn't. So most of it probably did. You're going to assume all of it did. So before you had manganese sulfate with water in it. Now you have manganese sulfate with no water in it after you heat it. So the sample mass after heating, right? So for number 2 is and then I should put mass up here, but it's crucible mass plus MnSO4. Oops, let me mass, this is after heating, minus the empty crucible, right? You're removing the crucible out of the picture of mass. Right, and the reason you take your crucible measurement is because you're using it, you can't go in and tear your crucible, right? Like you can the weighing boats, right? It's in there and you can't just remove it, tear it, and then put it back. So you take the empty mass first. That's why we do that. All right, and this is the mass of MnSO4 after heating. Again, they put the H2O there, but we're assuming it's all gone. Okay. So 3, right, number 3 is just before minus after, right? I feel like that's pretty, usually self-explanatory, right? It's mass before heating minus mass after, right? It's lower after. Then 4, it says calculate the experimental mass. So thinking if I plug in numbers here, I don't think this will give too many people difficulty, so I won't plug in any numbers. If you have any questions, I know I put a number up here, but I prefer not to make a bunch of numbers for the crucible and then the heating after and stuff like that, since I don't want to mislead on what the mass percent would be or give away what it should be around. So I won't be plugging in any more numbers for these. All right, number 4 says calculate the experimental mass percent of water in your sample. Use the formula, right? So you're just plugging that in. It is quite literally, right? Just plug and chug. Your initial minus your final. So that is from step 3, right? Divided by the initial times 100. So this is step 3 answer divided by initial mass times 100%. All right, now this number 5, right, it says to calculate the theoretical mass percent. And we did this in discussion, right? Where you're going to find how much the water contributes to MnSO4, right? So again, I can't plug in actual numbers here since you're going to have to do this. But find water's or H2O contribution to the molar mass. That'll be the hint. All right. So find that. You'll do something where we did it in discussion, or check your notes from lecture. This one I cannot give away. Then last but not least is 6. It says use the formula for relative error, right? And then it is the same thing. So let me take this just to clear this up, right? 5, the answer to 5 is your theoretical percent mass. And then your answer to, I believe it was 4, is your experimental percent mass. Okay, and then that is it for this lab, right? I'm not going to plug in the numbers. It is very much, I mean, not even very much, it is exactly the same, right, as that last one with the water and density. It's just that you're using different numbers here, right? So experimental is your experimental result for the mass percent, and then accepted value is theoretically what it would be. So it's pretty much the same, just different numbers. You're just plugging them in though. Okay, so I hope that helps. This is the end of this. There's no more. If you have any questions, right, shoot me an email. I'll be more than happy to help. So enjoy the rest of your weekend, and I will see you next week.